Hello, my name is TJ Glazier, and on behalf of myself, David Garland, and Bradley Schmerl, I'll be presenting on the automated management of collections of autonomic systems. Modern software systems, whether they are an enterprise web-scale application or an industrial power grid, are quickly becoming composed of individual subsystems which are, in and of themselves, autonomic. Each of these individual autonomic systems has a local goals and objectives that operate in a specific environment, and these systems are specialized to meet those goals in those environments. However, the collection of autonomic systems has a global level goals and objectives. The problem is, how do you improve the performance of the collection against the global goals and objectives while respecting the autonomy of the local systems? Typically, this job is left to humans to balance the global needs versus the local autonomy. However, this task is often exceedingly complex, and humans are often quite ineffective at doing it. One of the more straightforward approaches to resolving this problem is to introduce a higher level autonomic system which replaces the human administrators. We refer to this system as a meta manager. Now, we don't want the meta manager to subsume the control actions of the local subsystems. This would lead to a combinatorial explosion in the analysis, which would just simply be impractical to handle. Second, a meta manager needs to respect the autonomy of the local systems because they're specialized to the managed system and the local environment in which they're operating. And secondly, from a practical matter, we may not be able to directly control the managed system. Could be built by a closed box vendor or be hosted at a third-party partner. Okay, so we may not have direct access to the managed system. Unlike a typical autonomic system, though, the meta manager does have an advantage. Specifically, all of the subsystems under management are all in and of themselves autonomic and have an autonomic manager. This allows us to exploit the homogeneity in the type of objects being managed to make a certain set of assumptions about each of these items. We'll talk about the assumptions a little bit more when we get to the approach. So how are we going to get there? Well, we wanted to show a proof point that our automated approach to the management of collections of autonomic systems is effective. So in order to do that, we are using an actual outage suffered by the Google Cloud Platform on June 2nd, 2019. And we believe that a meta manager could have partially, maybe completely mitigated the outage. Specifically, we want to know, would our automated approach have improved the performance of the network control plane in conditions similar to what GCP experienced? And second, will our automated approach scale sufficiently to meet the needs of an enterprise system similar to the one presented in the GCP case study? So how are we going to get there? So first, I'm going to go ahead and detail out the Google Cloud Platform outage. I'm then going to describe the details of our automated approach. I'll then present the experiments that we ran and the results of those experiments. We'll then have a brief discussion about the approach and the experiments themselves, and we'll discuss potential future work in the area. And finally, I'll present the conclusions. So, the GCP outage. Whenever a customer establishes a solution on any cloud provider, they have a wide variety of options available to them into how their network is set up. Everything from security to autonomous zones to which data centers to use, how packets are routed within their individual projects. This is pretty standard operations for any cloud provider. In order to handle the sheer volume of requests for networking configuration changes, cloud providers establish a system commonly referred to as a network control plane. What this network control plane does is take in the requests for changes to the configuration of the network, process them, and update the actual physical networking hardware that is involved in order to meet the customer's configuration demands. The network control plane for GCP is specifically and at least partially controlled by a maintenance manager whose primary job is to make sure that all of the server instances are up to date, patched correctly, things of that nature. So where did the outage occur? The outage occurred in the network control plane itself. When the network control plane failed, the Google Cloud Platform and its customers began to experience up to 100% packet loss. What happened? Well, at 11:45 a.m. US Pacific, an automated maintenance event started and began to shut down many of the clusters running the network control plane jobs. At 11:47 a.m., 2 minutes later, users began to be affected by packet loss. The networking configuration was no longer valid, and the Google engineers were alerted. Approximately an hour and 15 minutes later, at 1:01 p.m. US Pacific, the root cause had been identified, that the network control plane was no longer functioning. But the control plane configuration had to be completely rebuilt because it wasn't persistent. And approximately an hour later, at 2:03 p.m., the rebuilt network control plane configuration began to roll out. Finally, between 1 hour and 2 hours later, the network control plane came back online completely and service began to recover and function normally. What's interesting about this outage is that while the individual subsystems of the network control plane, each individual cluster was operating under normal conditions. It's a fairly standard thing for a cluster to be taken offline, updated, and then brought back online. There was no single individual subsystem that could have understood the global picture that the entire network control plane was offline. To each individual subsystem, this was normal behavior. So the Google engineers then conducted a postmortem to understand exactly what changes they should make. First, they turned off the data center administration software responsible for the maintenance events. Okay? They did that as a temporary measure to correct a few bugs and a configuration change they found in that system. They hardened the cluster management software to reject requests to deschedule jobs at multiple physical locations. In other words, it would have been just fine if the maintenance manager took the clusters down in data center 1 or data center 2. But not both. Finally, the network control plane will be reconfigured to handle maintenance events correctly and to persist its configuration so that if there is an issue, they can restart the network control plane without incident. All right, so what is our automated approach? Well, remember that we want to replace the human administrators, in the GCP instance, the Google engineers, with an automated system that would have detected this outage and potentially mitigated it. In order for the meta manager to effectively do this, we have to have some way of characterizing the individual subsystems, specifically the autonomic actions of those subsystems. So let's go ahead and discuss that. We have a subsystem manager. The subsystem manager has the potential states of the environment. It also has the potential states of the managed system. It also has a set of configuration parameters that it operates within. For example, the minimum or maximum number of servers online, or the maximum amount of money or power that is available at any given moment in time. The subsystem manager also has a set of adaptation tactics. And the subsystem manager's job is to determine which adaptation tactic maximizes the local utility function. When the local utility function is a function that takes the state of the managed system and gives it a score between 0 and 1, 1 being perfect. When the subsystem manager locates this adaptation tactic, it applies this adaptation tactic to the managed system, resulting in a new system state. With this characterization of the individual subsystem manager, we can then apply two assumptions to it to enable a meta manager. The first is that these configuration parameters exist and can serve as a control interface for the meta manager. In other words, the meta manager should be able to update what is the minimum number or maximum number of servers, or update how much energy or money is available to the subsystem manager. These configuration parameters influence the adaptation decisions that each of the autonomic subsystems make. And finally, the second assumption is that we can elaborate an adaptation policy for each of the subsystem's autonomic managers. Specifically, given their configuration, they and the state of the environment and the state of the managed system, what is the new state the autonomic manager will put the managed system into? That is expressed in the adaptation policy that you see here. All right, so this characterization of an autonomic subsystem manager allows us to also define the meta manager. Formally, we can define a meta manager as a tuple. Script U is a global utility function. Script P is the set of all the adaptation policies. Script C is the set of all sets of the configurations of the subsystems. Script E is the set of all sets of possible states of the environment. Script S is the set of all sets of possible states of the managed system. And K is a set of functions for global knowledge. I'm not going to elaborate on global knowledge at this point in time because we do not use it in the experiments themselves, but it is detailed in the paper. Finally, the point of the meta manager, its objective, is in this expression. Specifically, for each adaptation policy, find the configuration that maximizes the global utility function for that subsystem. Okay? And that's what this expression lays out. All right, the experiment results. We established an exemplar system that mimics as closely as possible as we could, given the publicly available information about GCP's network control plane. It was instantiated completely on GCP itself, using as many GCP native services as possible. The first thing to understand about this is that the primary metric we are evaluating is the unacknowledged time. Specifically, the amount of time a request, the oldest request is on the queue. Since the ideal measure for this metric is 0, we are calling this the inverse utility. Okay? Anything above 0 is worse than 0 itself. We also don't want to evaluate the utility of this system at a single point in time. We want to evaluate it over a period of time. In short, the integral under the curve, okay, for this particular metric. So we refer to this metric as the inverse aggregate utility. The maintenance manager, similar to the live system, has the ability to perform a rolling restart on any of the clusters, referred to in the Google parlance as managed instance groups. We created a load generator, which represents the environment, and it will generate 250 messages per minute for 30 minutes with a 5-minute warm-up and cool-down period. And finally, we make a scalability assumption. Okay? One of the ways in which we believe we could potentially scale our approach is in the GCP instance, is to take advantage of the fact that the individual subsystem clusters are practically identical. They're configured identically. The only difference is their physical instantiation. So one of the scalability assumptions that we could make for this particular context is that because the individual managed instance groups are identical, if a meta management strategy or a configuration change is found for one of them, that it should be applicable to all of them. We'll discuss more about that in a little bit. Now, for the purposes of analysis at the meta manager, this system was modeled as a stochastic multiplayer game in Prism Games. Details of the model can be found in the paper, but to give an intuitive sense, the load generator is modeled as one player, the environment. The network control plane, including the maintenance manager, is modeled as a second player, and the meta manager as a third player. And the goal of the game is to determine what strategy the meta manager can employ to maximize its return in the global utility. All right, so the experiments themselves. Remember that we want to show two things. Would our automated approach have improved the performance of the network control plane? And would our approach scale sufficiently to meet the needs of an enterprise system? To do this, we're going to evaluate the aggregate inverse utility over 4 scenarios. Normal operations, operations with a maintenance manager, and then 2 different scenarios with operations with a maintenance manager and a meta manager. One of them is the raw model with both managed instance groups modeled. The second one has our scalability assumption applied and has only one of the clusters modeled. Let's go ahead and take a look at the results. So these are the results under normal operations. No maintenance manager and no meta manager involved. The metric that we're most interested in is the aggregate inverse utility, which under normal operations resulted in a score of 1,137. If we then look at the scenario with the maintenance manager, we can see a rather significant both qualitative and quantitative difference. In this scenario, the maintenance manager starts maintenance on a rolling restart on the first cluster at approximately time 10. At approximately time 15, the maintenance manager starts a second rolling restart on cluster 2. As you can see, this results in a rather significant increase in the aggregate inverse utility up to 3,024. We then run a third scenario with the maintenance manager and a meta manager, okay, specifically with the 2 clusters modeled. As you can see, the maintenance manager again starts the maintenance at time unit 10, okay, by performing a rolling restart on the first cluster. And then the meta manager, quote, runs. Because of the size of the model and the number of states it produced with both clusters modeled, we were unable to run this in real time. So we pre-calculated the results and cached them into the meta manager for this particular run. At approximately time step 12, the meta manager evaluates the situation, selects this pre-calculated strategy, and at time step 15, the maintenance on cluster 2 does not occur. This results in a rather significant both qualitative and quantitative difference, resulting in an aggregate inverse utility score of 1,157. If we compare these results to answer the question, would our automated approach have improved the performance? What we find is that between normal operations and operations with just a maintenance manager, we see a 166% increase in the aggregate inverse utility score. When we add in the meta manager, we see a 61.7% decrease in the aggregate inverse utility. This results in only a 1.75% increase or difference between the aggregate inverse utility score under normal baseline operations and with both a maintenance manager and a meta manager involved. In this particular context, we don't believe that 1.75% is significant. Therefore, we conclude that our automated approach would have improve the performance of the network control plane in conditions similar to what GCP experienced. However, that conclusion is predicated upon the fact that we pre-calculated the results online. The second question is around scalability. So if we then take the model and apply our scalability assumption that because the clusters are practically identical, if we find an adaptation strategy for one or a configuration change for one, that it's applicable to all, whether there's 2 or 200 subsystems. So we then modify the model and have only one cluster modeled. And in that situation, again, the maintenance event starts and against cluster 1 and a rolling restart is performed. The meta manager then runs live approximately between minute 10 and minute 13. It then calculates the adaptation strategy, applies it, and a maintenance event does not occur on the second cluster. This results in an aggregate inverse utility score of 1,095. Now, if we compare these two scenarios, what we find is a 5.4% difference in the aggregate inverse utility, which in a lot of contexts that might be significant. We don't believe it to be significant in this particular context. However, the big difference is in both the model runtime and the model states. The original model required just under 11 minutes to run and generated nearly 12.3 million states. The new model is significantly shorter, running in a little over 3 minutes and generating only 2.7 million states. All right, discussion and future work. Scalability. As we saw in the experiments, the scalability does present a bit of a problem. And this experiment showed one potential technique by making an assumption specific to the context that a strategy for one cluster is good for all clusters. However, there's nothing about our automated approach that mandates a specific analysis technique. In this situation, we chose a stochastic multiplayer game. But you could have chosen a technique that does non-exhaustive state space exploration, like a Monte Carlo analysis. Okay? You can choose which analysis technique would be appropriate for your specific context. This allows for adaptation of the meta manager itself to a wide variety of contexts and performance demands. Future work in this area, specifically a better understanding of the applicability of various analysis techniques, investigate how global knowledge can improve the effectiveness and scalability of the approach, and loosening the goal of improving aggregate utility to improving against a global objective. So in conclusion, we are able to develop an automated approach, but will it help in a realistic scenario? We have a realistic scenario with significant impact, and the approach was able to generate a strategy that might have mitigated the outage that was suffered by GCP and would be sufficiently scalable to this enterprise system. On behalf of myself, David Garland, and Bradley Schmerl, we would like to thank you for taking the time to learn about the automated management of collections of autonomic systems.